Welcome back to Blueprint to Reality. Today, we're talking about something that sounds like a contradiction, but isn't. Tensile structures. How can something be lightweight yet incredibly strong? Get ready to discover the engineering magic behind these seemingly delicate but super durable structures. From iconic sports arenas to futuristic airports, tensile structures are popping up everywhere, and we're about to reveal why they're changing the game in architecture and engineering. What are tensile structures? First off, what are tensile structures? Imagine a fabric stretched tightly between 2 points. The material itself may not seem strong, but when tension is applied, it becomes incredibly rigid and can support huge loads. Tensile structures rely on tension, not compression, to stay stable. Unlike traditional buildings that use heavy materials like concrete or steel to support themselves, tensile structures use flexible materials like membranes or cables to create lightweight but super strong designs. The power of tension. Okay, so how does this work? Think of a suspension bridge. Those cables are under constant tension, and it's that tension that holds up the massive weight of the bridge. Tensile structures work in the same way, but instead of just cables, we use high-tech materials like EEFE, PTFE-coated fiberglass, or PVC-coated polyester. These materials are flexible when loose, but can become rock-solid when pulled tight. Efficiency in design. Here's the genius part. Tensile structures are incredibly efficient. They use less material, meaning they're lighter and cheaper, but because they distribute forces evenly through tension, they can cover massive areas without needing heavy support columns. That's why you see them in places like stadium roofs, exhibition centers, and pavilions. Ever been to the Denver International Airport? That iconic white canopy is made from tensile membranes, and it's strong enough to withstand heavy snow and wind, all while looking sleek and modern. Advantages over traditional structures. So, why go tensile over traditional methods? For one, flexibility. Tensile structures can be stretched into complex, flowing shapes that would be impossible, or insanely expensive, to achieve with steel or concrete. Also, they're lightweight. This means you can cover large spaces without adding massive loads to the foundation. And get this, they're more eco-friendly. Less material, faster construction, and a lower carbon footprint. Real-world examples. Now, let's talk about some jaw-dropping examples. Check out the Millennium Dome in London. It's 320 meters in diameter, and its entire roof is supported by nothing more than steel cables under tension. Or the Allianz Arena in Munich. Its outer membrane is made of EDFE, and it's strong enough to handle extreme weather while being so light, it barely adds any weight to the structure. And it looks futuristic as heck, too. The future of tensile structures. As materials technology keeps improving, tensile structures will only get more impressive. We're talking about lighter, stronger, and more flexible designs that can be used for everything from disaster relief shelters to space exploration bases. So, next time you see a massive canopy or a sleek, curved roof, just remember, it might look light, but thanks to the magic of tension, it's tough as steel. That's it for today's episode of Blueprint to Reality. If tensile structures blew your mind, smash that like button, hit subscribe, and drop a comment on your favorite engineering feat. Thanks for watching, and we'll see you next time. Welcome to Blueprint to Reality. Today, we're diving into one of the most fundamental principles of structural engineering, load distribution in buildings. Every structure, whether it's a small house or a towering skyscraper, is designed to bear and distribute loads efficiently. Understanding how this happens is key to creating stable, safe, and long-lasting buildings. Let's break down the art of load distribution into simple concepts. What is load distribution? At its core, load distribution refers to how the weight, or load, in a building is spread across various structural elements. These loads come from everything: the materials used in the building itself, the furniture inside, and even external forces like wind or earthquakes. A well-designed structure ensures that these loads are evenly distributed so no part of the building is overloaded, which could lead to damage or even collapse. Types of loads. There are several types of loads that a building must handle. 1. Dead loads. These are permanent loads, like the weight of the building materials, concrete, steel, walls, floors, anything that remains in place throughout the life of the building. 2. Live loads. These are temporary or movable loads, such as people, furniture, or even snow on the roof. 3. Environmental loads. These include forces like wind, seismic activity, earthquakes, and even temperature changes that can cause expansion and contraction. Each type of load must be considered during the design process to ensure a building's stability. How load distribution works. Now, how does a building actually distribute these loads? It all begins at the roof and upper floors, where loads are first applied. From there, the loads are transferred to beams and columns, which act like the skeleton of the structure, carrying the weight downward. Next, the loads are transferred to the foundation, which spreads the load evenly into the ground. Think of it like a funnel. Loads move from a wide area at the top to smaller, concentrated points and then spread out again into the ground, preventing the building from sinking or shifting. Designers often use techniques like cantilevering, where part of a structure extends without support, to balance the load and prevent excess weight from accumulating in one spot. Importance of balanced load distribution. Why is all of this important? Simply put, balanced load distribution prevents structural failures. If a building's load isn't properly managed, you could have buckling columns, cracked walls, or uneven settling, all of which can lead to catastrophic results. So, next time you look at a tall skyscraper or even your own home, remember that there's an intricate system at work underneath it all, carefully designed to distribute and balance loads to keep the structure standing tall and strong. Thanks for tuning in to Blueprint to Reality. If you found this breakdown helpful, be sure to subscribe for more insights into the world of structural engineering.
See you next time.
Welcome to Blueprint to Reality. In today's episode, we're tackling a critical topic for cities prone to earthquakes: seismic retrofitting. As the risk of earthquakes continues to challenge engineers, retrofitting is the solution for making older buildings and structures more resilient to seismic activity. But how exactly do engineers strengthen existing structures, and why is it so important? Let's break it down. Why is seismic retrofitting needed? First, let's talk about why seismic retrofitting is crucial. Many buildings were constructed before modern seismic design codes were in place. These structures, whether they're schools, hospitals, or bridges, are vulnerable to collapse during an earthquake. Without retrofitting, these buildings pose a huge risk to human life and infrastructure. Seismic retrofitting helps bring older structures up to today's standards, ensuring they can better withstand the powerful forces generated by earthquakes. Identifying weak points. The first step in retrofitting is to identify weak points. Engineers conduct detailed assessments, looking for structural vulnerabilities like soft stories, inadequate connections, or materials that don't respond well to seismic forces. For example, older concrete buildings often have weak connections between floors and walls, making them susceptible to shear forces. By identifying these vulnerabilities, engineers can develop targeted strategies to reinforce the structure. Common retrofitting techniques. Once weak points are identified, engineers employ a variety of retrofitting techniques to strengthen the building. Let's look at a few common methods. Base isolation. This involves placing flexible bearings or pads between a building and its foundation, allowing it to move independently of ground motion. It's like giving the building shock absorbers to cushion the impact of an earthquake. Shear walls. These are walls added to resist lateral forces. By increasing a building's lateral stiffness, shear walls help reduce the swaying motion that can cause collapse. Bracing systems. Engineers may also install steel or reinforced concrete braces to add rigidity to a structure, preventing excessive movement during seismic activity. Column and beam jacketing. Wrapping or jacketing columns and beams with materials like steel or carbon fiber strengthens them, increasing their load-bearing capacity and preventing failure under seismic forces. Impact of retrofitting. Seismic retrofitting isn't just about strengthening a structure, it's about saving lives and protecting essential infrastructure. Take the example of schools, hospitals, and emergency services buildings. Retrofitting these structures ensures they remain operational after an earthquake, providing critical services when they're needed most. Retrofitting also reduces repair costs in the aftermath of a quake, making it a long-term investment in safety and sustainability. Seismic retrofitting is one of the most effective ways engineers can protect communities from the devastating impact of earthquakes. By reinforcing existing structures, we not only preserve our infrastructure, but also safeguard the lives of those inside. That's the power of engineering in action. Thanks for watching Blueprint to Reality. Be sure to like, subscribe, and hit the notification bell for more insights into the world of civil engineering and structural design. Stay safe, and we'll see you in the next video.